Okay, thank you for attending our webinar today. We will go ahead and get started. So today we're going to be talking about failure rates and the differences between generic failure rates, specific failure rates, and composite failure rates, and what would be best for your design situation. My name is Lauren Stewart. I work at exida, and I am working primarily on their mechanical customers. I do certifications and FMEDAs, safety cases, but I also do research in 2H, stiction, and failure rates. A little bit about who we are to start the webinar off, in case you do not know exida. We are a global company, no matter where you are or your suppliers are or your customers are. We have someone close by to help with any functional safety needs you may have. exida can be broken up into 4 main industry focuses. We have our OEM, our system design, end user, and engineering contracting sides of us. We have people to help you with your functional safety needs. We have classes and trainings to teach you anything you might need to know in functional safety, but we also have tools to help with each industry focus. For our engineering and contracting consulting services, we not only work in functional safety and process safety, but also in alarm management and cybersecurity. And as I said, we have a bunch of tools for functional safety, with all of their purposes being to save you time and money while increasing efficiency and productivity. We have exida certification, and we certify products from IEC 61508, but also we certify systems in IEC 61511. We have our machinery and our tool qualification certifications, our cybersecurity, and our personnel. But the reason we're here today is to talk about SIF design, to talk about different failure rates and compare all of them together with real-life examples using exSILentia. So let's go ahead and get started. When I like to start off webinars, I remember what it was like when I first got into functional safety, having a lot of questions and realizing there's a ton of information out there, but what's right? What should I believe? What should I not? And it's very overwhelming. So I like to start off my webinars with a little bit of an introduction to the subject, just in case you're not familiar with some of the terms or topics that we're talking about. And today's webinar, I thought it'd be best to start out talking about what is SIL. You may have heard of it before and not quite know what it all entails or what it even stands for. But SIL talks about safety integrity levels. And it deals with functional safety and the standards. So it all started with IEC 61508, which is the umbrella standard of the functional safety world. And people from a bunch of different countries got together and said, we need to make one standard that everybody should use dealing with functional safety. And IEC 61508 was written. But there are some areas where you might need further instruction or further details or requirements. So under IEC 61508, there are specific industry sectors You're going to have your nuclear sector or your machinery sector, or for end users, you would use the process industry sector or IEC 61508. And all of these specific standards complement IEC 61508. So they don't contradict. If you see information in one, you will see the information in IEC 61508 as well. And when I was starting out, and when I've heard other people started out in functional safety, well, you find out it was written for an EEPE-based system, and that stands for electrical, electronic, or programmable electronic device. So the question we get often asked, well, then I just have a final element or a simple mechanical device, or I have a valve. Does my valve need to be certified for IEC 61508 or certified in a system for IEC 61511? And the answer is, well, I tell people to do what I just do, is just Google it. So in Google, I typed in IEC 61508 and mechanical elements. And one of the first things that pop up is the IEC 61508 website and their frequently asked questions page. And the fourth question, so you can tell it's been asked quite often, talks about if mechanical devices should be used or not. So I can't read that fine print, so I zoomed in. And this is basically telling you, yes, mechanical devices or simple devices, type A devices, a valve, final elements, anything like that, should still be safety certified. It just doesn't mean you have to follow every single part of the standard. If you have a valve, you do not need to meet the requirements for coding or software. That just doesn't make sense. So you can filter on the low complexity questions, and for a simple mechanical device, meet only the requirements that apply to your application or your product. Safety integrity level, it's defined as a 1 to 4 level rating from IEC 61508 and 511. And this is, you have SIL 1 being the lowest safety integrity level, where SIL 4 is the highest. And that doesn't mean that the products are not equivalent. That means that they were audited for more requirements, where SIL 3 had to meet the requirements for SIL 1, SIL 2, and SIL 3. It is possible that just somebody had not gone through the process to meet the other requirements. And a safety integrity level is basically making sure your system or your safety instrumented function performs the job that it needs to do, and it manages the risks it's supposed to manage. So now you know what a SIL rating is. Now I'm just going to quickly talk about what the products that you're buying had to go through to meet the certification, and why it's not just no big deal. It was a lot of hard work that they went through, and they're usually pretty proud of it. They have to make sure that they are assessed and complete the assessment for systematic capability rating, the architectural constraints, and the Pfd average. And only when you meet all 3 of those requirements and can fully check off that you pass, are you going to be compliant for that safety integrity level. So they could be doing a great job out of 2 out of 3 of these and not be doing one of them, and they would not be able to say that they are compliant with the standard. Systematic capability, the first thing that they're judged on is their quality system. They'll have somebody audit their quality management system per IEC 61508. And whether they're going for a SIL rating of 1, 2, or 3, there are different number of requirements that need to be met before that they can say that they are that SIL or SIL capable. And this is, when you see a certificate, this is that big, I'm a SIL 2 product, or I'm a SIL 3 or a SIL 1 product. That's what you're going to see on a certificate, is their systematic capability. The next circle are the architectural constraints, and this is applied by either following Route 1H or Route 2H from the standard, which is once again described in IEC 61508. Route 1H is by following the SAFE failure fraction. Route 2H is a proven in use or the history of a product. So they need to say which direction they're following and make sure that they meet all of the requirements from that route for the device and for the entire SIF. And then finally, the Pfd average calculation. And the Pfd average calculation is based on a number of variables, including the dangerous failure rate. So the device that you're buying will go through the process of having an FMEDA done, and you will receive your failure rates from that report or the certificate. The manufacturer should not give you a Pfd average calculated number for their device alone, unless the device is an entire system. Because there are so many variables going into the Pfd average calculation, such as things that you control as an end user, such as mission time or your proof test, your maintenance, there's so many things that they would have to assume and make those variables, what the values for those variables in the calculation to be, it's not going to be relevant for your exact system. So we highly encourage you as the end user to do the Pfd average calculations yourself, but using the failure rate data from the manufacturer. So that being said, now you know how a device gets certified in a very, very, very quick manner. Now, why do you need this? Well, the safety integrity level rating is used in 4 different ways. You can use it to establish the risk reduction requirements. You can use it to set the probabilistic limits for hardware random failures. You can use it to figure out your architectural constraints, and also to establish the systematic capability for your SIF. We're going to go ahead and look a little bit deeper into a few of these and then move on to exSILentia real examples of different ways to view your system. So the first way we're going to look is to establish your risk reduction. And the best way I learn is through examples. That's why I set this webinar up the way I did. But the risk reduction, the way I explain it is through an example. So say you've done your PHA and it determines that this specific hazard can occur once every 10 years, causing a major release of toxic fumes into the atmosphere. I don't know about you, but I usually consider that bad. So the question is to determine the risk reduction factor needed for the hazard to occur once in every 500 years instead. And that simply is to take that 500 years, divide it by the 10 years you currently have. So you are going to need a risk reduction factor of 50 in this example. You take that number and open up IEC 61511 and see this safety integrity level compared to risk reduction factor table. And there are two ways to interpret this table. First, you can be a little conservative and say, well, I need a SIL2 SIF here, because that, for a SIL2 device, that's going to have a risk reduction between 100 and 1,000. So I know no matter what device I pick, if it is SIL2, it's going to have enough risk reduction that I need. Or you can say I need a SIL1 rated device with a risk reduction factor of at least 50. The next thing you can do with your SIL rating of this SIL device, you can set probabilistic limits for hardware random failures. And that is to look at the probability of failure on demand, or if you've heard Pfd average being used. And you can say, well, I have a SIL2, I'm going to fall into this Pfd mode, or I need this Pfd mode, I'm going to need a SIL2 rated device. And I mentioned briefly about the variables in a Pfd average calculation. And these are just some examples of things that are going to need to be entered. And as you can see, the FMIDA would be handled by, or the dangerous undetected failure rate would be handled by the FMIDA, but things like proof test coverage, proof test intervals, mission time, all of that you're going to need to provide for the Pfd average calculations. So let's get into the examples. And as I said, these are real life using exSILentia. So I did this morning, and I wanted to show you what a SIF looks like using a specific pressure transmitter that is certified. And I just picked any one that I found this morning, and I made a SIF with a specific pressure transmitter in a specific process. It's a clean service. I configure the trip, all of that information. And as you can see from this, I was able to create an output. And from this entering a specific sensor, I was able to find the Pfd average for the sensor, the logic solver, and the final elements with other variables entered, obviously, of 3.49 times 10 to the negative 4. And you can see that this is a SIL2 Pfd average capable Pfd. On all of the examples, I wanted to keep just everything the same and just change one variable. So the next example I want to look at is keeping the logic solvers, the final elements, everything the same, except this time we're going to look at a generic safety transmitter instead of the specific one we chose before. So we were able to enter the generic information in here, and everything else stayed the same. Just changing that, you can see our Pfd average for the sensor, it changed by an order of magnitude. And now we are just considered a SIL 1. So that was a major difference. But I understand how when you're designing your system, you might not know exactly what device you're going to use. So that's why we wanted to give you a third option. And I am suggesting to create a composite, say X. Once again, this was just random pressure transmitters that we looked at this morning. But here are 3 separate pressure transmitter datas from actual FMEDAs. We looked at all of them for the low trip, high trip, detected, and then dangerous undetected and safe undetected failure rates. And for each one, say you have 2 options or 4 options, I just picked 3. You take your most conservative number. So for example, this low, we have 44, 51, and 52. So for my composite, I'm going to say my low failure rate is a 52. For high, I picked 87. For the detected, 622. For the dangerous undetected, 75. And the safe undetected, 81. And from that, I was able to click the user-defined portion in exSILentia and enter my composite X information for the safety transmitter. Once again, the logic solver, final elements, everything stayed the same. I just changed this sensor information. And this time, we have a Pfd average not as good as the specific device, but it's at the same time not an order of magnitude off as the generic or high as the generic. And that it will save me from claiming SIL 1 to SIL 2 in this system. And say you have 4 or even 3 sensors that you may be using in this system. And say you're most concerned about your high trip value, or in this system, you're most concerned for your Pfd average, or maybe you might be most concerned about spurious trips. Whatever that may be, you can find the 1 or maybe 2 devices that have thrown you over, and maybe eliminate those, and you can still have 2 or 3 devices in your composite, yet still achieve your needs. So when you are still designing your system, you don't know exactly what you want to design with, but you do maybe have a list, or you do know what you're going to need, you can use composites as a solution for you. However, some people, you have to also be careful when you're doing composites or when you're doing any type of calculations with data presented to you. And when you're doing calculations, your calculations are only as good as the data that you received. So if you have good data, your calculations are going to be good. If you received bad data, your calculations are not necessarily going to be appropriate. I wanted to give you one more example just to show what the difference between good or maybe overly optimistic data can do to your calculations. So this is an actual certificate that we saw, and it lists the failure rates and also the demand per year and all of that. And from that, we were able to do an exSILentia for this system. Unfortunately, this wasn't for a sensor. This was for a final element. So the example that we are using, this is a complete different example before. So this was actually a certificate for a final element. So the first thing I want to point out is the pie chart on the left-hand side. And in this pie chart, you can see that the final element slice, or the bluish purplish color, is actually only 5% of the total. So that's great, because I usually find that final elements take up 50% or even more of the PFD contribution. Next, I want to talk about, you have your PFD and your SIL level from that PFD, and it says you achieve a SIL 2 with no redundancy and no diagnostics. You can just put it in there for 10 years, never test it, you're good to go. Well, that's wonderful news. You can be really excited at this point, until you get down to the bottom and you see 12 fits. Well, you might not think of fits every day in terms of fits like I do. So what does 12 fits mean? Well, that's for the whole final elements. That's your valve, your actuators, your solenoids, anything you're throwing in your final elements of the SIF. So you're saying that your valve will not have, or solenoid will not have, an error or a trip in 9,458 years. Oh wow, that's interesting. Or if you want to, you can look at it a little differently. If you had 9,458 valves in your plant, or SIFs in your entire plant, you're only going to have one failure a year. Well, I'm not sure if I've just worked in different plants than you have, but that doesn't quite pass the smell check for me. It's something that might raise a red flag in my eyes. So we then, oh, stop, don't use that. Raise a red flag if you see something like that. So if we then did the same example, but we used more realistic failure rates from silsafedata.com. And we were able to keep everything else the same, the sensor and the logic solver. And as you can see the pie chart, now the final elements are the significant contributor to PFD average, which you can expect. Your PFD average, unfortunately, has not become as good along with your SIL rating, but this is much more realistic, and you can improve that through diagnostics, or you can improve that through testing. All of these things can be changed. But anyway, then you have your PFD average. The final elements, so the logic solver, or the final elements, the valve, actuator, solenoids, are now 1,300 fits, or 87 years. So your valve won't have an accident in 87 years, or more likely you have 87 valves in your plant and you're going to have one trip a year. That seems much more realistic to me than having thousands upon thousands of years without having an issue. So in summary, we understand that composites might not work for every one of your examples, or you might know exactly what you need. But if you don't have your design needs figured out yet, and you don't want to use generics and have an very high failure rate, use a composite. Pick 2 or 3 and take the conservative number and make your composites, run your own exSILentia, and then you can see how much compared to a generic you're going to save. And it can be an order of magnitude difference. And at the same time, if you get unrealistic data, don't just simply use it. Raise a red flag. It can be dangerous in some situations. And if you are doing those type of things, using SIL certified devices, being realistic with your failure rates, you're really going to be seen as a market leader. I'm going to now go ahead and see if there's any questions that came out. And if you think of any later, there's a few in here. If you think of any later, please feel free to email them to me, and I will get back to them as soon as I can. The first question is talking about the proven in use items, and in exSILentia when you can check off proven in use. That is a great question, and that is an actual webinar and blog topics that we have talked about previously. That is something that that question alone would be a full webinar. If you want more information on this, please go to our YouTube channel or our website, and we have webinars on this topic alone. When you're talking about failures per year, are you referring to mean time to fail spurious or dangerous? When I was speaking, I was talking about the mean time to fail dangerous. In exSILentia, there are mean time to fail spurious in the calculations, but when I was speaking out loud, reading, interpreting the things on my slides, I meant dangerous. Does anybody else have any questions? Well, if you think of any later, please there was a question about CFSE, and if you'd like to, you can email me directly. Since it doesn't have anything to do with this webinar, I'm going to pass that off through email. So please, if you have any other questions, let me know, and thank you for attending.